Alright, for this video I'm going to talk about Bode Plots, and I'm going to talk about what they're for and sort of how they can be used as a tool for stability. So the Bode Plots can kind of do two things. One is they tell you the frequency response of a system, but they can also tell you stability. Okay, so first let's just look at like open loop control of a simple first order system. Okay, so I've already done a video on a system like this, tau is plus 1 over 1, and I'm going to call the input U. I'm going to leave a little bit of space, call the input U, and then the output X. Okay, and so I've already shown a video on how to draw first order Bode plots with this, and basically your tau here is 1 over the cutoff frequency, and so your cutoff frequency is 1 over tau. And so if you plot a Bode plot where you plot magnitude, and I'm going to plot magnitude just in magnitude, not dB. And so the DC gain is 1, and so that would be 0 dB, but I'm going to draw 1. And this is going to drop off at here at 0.707, which is minus 3 dB, is here. And that is going to be the cutoff frequency of 1 over tau. And like I said, I have another video that shows how to do that. So then if you look at the phase plot, it is 0 degrees at 0, I think. Yeah, 0, and then it goes to minus 45 at the minus 45 here at the, that's a terrible drawing. So if they draw the cutoff frequency here, and this here, right here, minus 45, and then when it goes off to infinity, it hits minus 90. Oh, that's a terrible graph. Okay? And so yeah, that's fine. What this is telling you is that if U is a sine of omega t, okay, where the input is some sine wave and some frequency, okay, the output X, steady state, and the reason why I write steady state is because whenever you hit a dynamic system, you're going to have a homogeneous response and you're going to have a particular response or the forced response. And so when I write X steady state, I mean once all the transients, once all the homogeneous part has sort of died out, unless this system is stable, then the output is going to be the same for all time, so long as the input is this. And what this is going to be equal to is MA times sine omega t minus this phase shift, okay? And so what this means is that if I put in a DC gain of 0, my steady state value is going to be the same, right? I'm not going to scale the output because M is 1, and I'm not going to have any phase shift. Now granted, if omega is 0, my input is just A, so my output will just be also A, my steady state output, okay? Now as I increase my frequency of my input, my gain M is going to decrease, which means my output amplitude is also going to decrease, okay? And so that's sort of what a Bode plot tells you, just in a nutshell. It tells you how much your output is going to lag your input, and it's also going to tell you how much your system attenuates a signal, right? So if you want to design, say, a low-pass filter like this and you want to filter out some high-frequency noise, you could design a filter like this because the output is going to essentially be attenuated out here. So those high-frequency signals are going to get attenuated and get smaller. In terms of stability, though, you kind of have to look at gain and phase together, okay? So let's take, I said I was going to draw this small, but let's go ahead and close the loop on this. So I'm going to put X command in here. I'm going to put my error signal, and I'm going to put a gain block K, and then I'm going to do 1 over tau S plus 1, and I'm going to feed it back like that, okay? Now if I asked you the question and I said, what are my limits on K such that the system is stable, okay? Now you have two ways to do this. Number one is you can close the loop and do a route table, Number two is you could do a root locus, and you could look at the poles. Number three, and this is what you don't know how to do yet, and this is why you're watching the video, is you can actually do a Bode plot. Now, I've done this problem before, but I'm going to tell you right now that just by looking at this graph, I can tell you that this system will never go unstable so long as k is positive, okay? And number one and number two are going to take a lot of work, but number three, you can just look at the graph. Now granted, I guess you had to generate the Bode plot, so I guess you can't necessarily argue that it's the fastest, but if somebody gave me a Bode plot, I could immediately look at it and say it's never unstable, okay? So let's go back to that and see why that is. So first, let's look at number one. So let's close the loop and do a Ralph Hurwitz table, okay? So if I close the loop, this is C, this is G, H is equal to 1. My closed loop transfer function is CG over 1 plus CGH. So I'm going to get K 1 over tau S plus 1 over 1 plus K 1 over tau S plus 1 equals, if I multiply by tau S plus 1 on the numerator and denominator, I'm going to get K over tau S plus 1 plus K. And so my denominator, right, my denominator is what I care about, is tau S plus 1 plus K equals 0, okay? If you do a Ralph table on this, you're going to get S to the 1, S to the 0, and so you're going to do first value skip 1, which is going to be tau, skip 1, 0, and then you're going to do 1 plus K, skip 1, 0. And so I guess I was a little bit wrong. You can actually make K negative and it still won't go unstable. Is that what's going on? Okay, that's fine. So I guess that in this case, tau is always greater than 0, 1 plus K is always greater than 0, and so K can be, has to be greater than negative 1 to be stable, okay? This is a first order system, so you can actually just solve for this. And so you can say tau S plus 1 plus K equals 0, and so that means S is negative K plus 1 over tau. And so if you want this, you need this to be negative, so K has to be greater than negative 1. So in two different ways, you can get it that way, okay? But the other thing that you can do is you can do a root locus, right? And so a root locus, what you do, I'm kind of running out of space here, so let me grab my phone and take a picture of the board. Let's see. Okay, so while that's uploading, I'm going to go ahead and erase this. So you can also do a root locus. And the way you do a root locus is you need to look at the closed loop transfer function, which is CG over 1 plus CGH. And what you really care about is 1 plus CGH, okay? And what you do is you write 1 plus CGH equals 1 plus KL equals 0. And we did this already. This is 1 plus C was K, and then H was 1, so this is just 1 over tau S plus 1. And so then obviously L is this transfer function here. When this is 0, your poles are undefined, okay? And so this is sort of the solution of this gives you your poles, okay? And so if you want to draw this root locus, what you do is you draw the roots and zeros of, or the poles and zeros of this polynomial, and so you're going to get tau S plus 1 equals 0, and so S equals negative 1 over tau, and so you get this here. And again, remember that was our cutoff frequency, right? So everything kind of like is shaken together. There's so many different similarities between everything. And so this is our open loop pole. If we do our Ralph test, our real line test, everything over here is 0, which is even, so this is not part of the root locus. Everything over here, this is 1. There's 1 pole to the right, so that's odd. So everything here is part of the root locus, okay? And we could do the asymptotes and things like that if we wanted to, but there would only be one asymptote, and it would be 180 plus 360L. And n minus m is 1, and so it would just be 180. So you have one asymptote at 180. And you can easily see from this root locus that this system never goes unstable. Okay? So how do you read the Bode plot and determine that the system can never go unstable? Okay? Well, think about it this way. If I take my transfer function and I close the loop, my system is now GCL, and my output is X. Okay? So now my input command is XC. This is going to be A sine omega t, and my output is going to be MA sine omega t minus phi, right? Now, for your system to go unstable, this M here needs to blow up, okay? And what really happens is that there's a scenario where your system can't keep up. Your system lags behind so much that your system just blows up and goes unstable. In this case, for M to go to infinity, what actually happens is you need 1 plus CGH to go to 0. It's actually at any of your poles, but in this case we're not looking at our poles because we're in the frequency domain. What we really care about is 1 plus KL in the frequency domain equals 0. So if we're in the frequency domain, how does this work? Well, it means KL has to equal -1. Well, what's -1 in the gain and phase realm? Well, the gain of 1 the gain of -1, the gain of -1 is 1, and then the phase of -1 is 180 degrees, minus 180, okay? And so in that case, I'm going to move to this side. In that case, our Bode plot can show us where, because we're looking at frequency now, what frequency does our system go unstable, okay? And the instability that we're looking for is a gain of 1 and a phase of minus 180. And so now you can see why when I drew the first order Bode plot, right, if I draw gain, so this is frequency, this is a gain of 1, here's the cutoff frequency, and here was the phase, right, so this was minus 45, and this was minus 90. There is nowhere on this plot where the gain is 1 and the phase is minus 180. The phase only goes to minus 90. So you can never make a first order system go unstable because you can never get into this scenario. Now, if your K is negative, Bode plots, like you're looking for positive margin here, right? And so I'm going to make this a two-part video because this is getting kind of long. But the idea is, at least in this case, this system can't go unstable. So in the next video, let's look at a second order system and a third order system, and let's look if we can actually plot some gain and phase margins and see if we can get stability from that, okay? So this is basically just going to be an overview video, and I'll post another video on some more concrete stuff, okay? Here we go.